Participants, please mute your audio. I request participants to mute your audio. And also, please don't present the screen. Samartha Nayak, please don't present the screen. We'll have problem here if you present the screen. Am I audible, Samartha? Hello, sir. Samarth, please stop presenting because we want to display our brochure. Samartha Nayak. Sudhindra, am I audible? Guru Prasad, please put YouTube live link in the group. Emerging trends in group 1 and group 2. Please put my this YouTube live link in the group. Emerging trends.
Hello.
Good morning, sir.
Hello. Bharat, am I audible?
Yes, sir. You are audible.
Okay. Okay. Hello, Bharati.
Yes, sir.
I'm
Yes, sir.
I'm entering through with Siddiq sir's mobile. There is
Okay,
some
sir.
problem over here. Yeah.
Okay, sir.
Yes. I'm ready.
Yes, sir. Okay.
ಈಗ ಒಂದು ನಿಮಿಷ ಸರ್.
Yes, I can hear you, sir.
Yes. Okay.
Yes, sir. We can see you. Principal, sir, we can see you.
Yeah, I'm ready. Fine.
Yes, sir. Shall we start after 3 minutes? Because people are getting in.
Yes. We can start after 10 minutes. Fine.
Pratheek sir has joined, right? Pratheek sir? Yes.
I don't know.
Yes. He's here. Guru Prasad sir, please post YouTube live link in both the groups, Emerging Trends 1 and Emerging Trends 2. Also in our forum, college forum group. There is a resolution, this one resonance because there are two computers together. Two mobile phones are with a less than minimum distance. Distance.
ದೂರ ಇಟ್ಕೊಳ್ಳಿ.
Shall we start, sir? It is 10:30.
Yes, yes.
Sure.
I'll just inform the participants. Yes. Manisha Madhak. Sudhindra, did you stop getting requests? Because still few people are in the queue. Okay, we will start with the program. Manisha Madhav, please check your screen. You are trying to present. UCM library. Okay, fine. Good morning, everyone. I hope you are all keeping safe and well through the outbreak of COVID-19 pandemic. I, Dr. Bharati Pillar from the Department of Computer Science, hereby take this opportunity to welcome you all to the inaugural function of International Webinar Series on Emerging Trends in Intelligent Computing and Informatics. The objective of this webinar series is to introduce the basics of cutting-edge technologies like artificial intelligence, machine learning, natural language processing, machine vision, Internet of Things, cloud computing, and biometrics. The first episode of this series is application areas of artificial intelligence and machine learning. The objective of this episode is to introduce basic principles of various application areas of artificial intelligence and machine learning. On this occasion, we have with us our Honorable Vice Chancellor, Professor P. Subramanya Edipaditaya Sir, Sri Raju Magavira, Registrar of Mangalore University, Dr. Uday Kumar M.A., Principal, University College, Mangalore, Sri Pratheek Irvathur, NL Matics, New York, USA, our resource person for the day, Dr. Veerabhadrappa, IQAC Coordinator and HOD of Computer Science. It's my pleasure to welcome you all. I request all the participants once again to mute your audio throughout. Let us begin our program with the college anthem. This anthem, I'm happy to say that this anthem is composed by our principal, Dr. Uday Kumar M.A.
ಕದವ ತೆರೆದರು ಮಂಗಳೂರ ಮಹನೀಯರು, ಹೆಸರ ಹಂಗಲು ಮೀರಿ ನಿಂತರು, ಜ್ಞಾನ ದೇಗುಲ ಕಟ್ಟರು. ಹೆಸರ ಹಂಗಲು ಮೀರಿ ನಿಂತರು, ಜ್ಞಾನ ದೇಗುಲ ಕಟ್ಟಲು. ಜ್ಞಾನ ದೇಗುಲ ಕಟ್ಟಲು. ಮನಸ್ಸಿನ ಮಂದಿಯು ಕಟ್ಟಿ ಮತಿಯನು ಮುಟ್ಟಿ ಮನಸ್ಸಿಗೆ ಜ್ಞಾನ ಸಿರಿಯನು ಬೆಳೆಸುತ್ತ, ಕಟ್ಟಿ ಮತಿಯನು ಮುಟ್ಟಿ ಮನಸ್ಸಿಗೆ ಜ್ಞಾನ ಸಿರಿಯನು ಬೆಳೆಸುತ್ತ, ಜ್ಞಾನ ಸಿರಿಯನು ಬೆಳೆಸುತ್ತ. ಸರಿದಿದೆ ದೀಪ ಉರಿದಿದೆ, ಮನದ ಕತ್ತಲೆ ಕಳೆದಿದೆ, ಆಸೆ ಅಕ್ಷರ ಜ್ಞಾನ ಸಾಗರ ಹರಿದು ಎಲ್ಲರ ಎಲ್ಲಿಗೆ, ಆಸೆ ಅಕ್ಷರ ಜ್ಞಾನ ಸಾಗರ ಹರಿದು ಎಲ್ಲರ ಎಲ್ಲಿಗೆ, ಹರಿದು ಎಲ್ಲರ ಎಲ್ಲಿಗೆ. ಪೊರೆಯನು ತೊರೆದು ಹೊಸ ಹುಟ್ಟರಿದು ಪಡೆದಿದೆ, ಹಳೆಯ ಪೊರೆಯನು ತೊರೆದು ಹೊಸ ಹುಟ್ಟರಿದು ಪಡೆದಿದೆ, ನಿತ್ಯ ನೂತನ ಬಾಣ ಚೇತನ, ನಿತ್ಯ ನೂತನ ಬಾಣ ಚೇತನ, ಕಲಿತ ಎಲ್ಲರ ಪಾಲಿಗೆ, ಕಲಿತ ಎಲ್ಲರ ಪಾಲಿಗೆ. ಸತತ ಕಲಿಯಲು ನಿತ್ಯ ನಲಿಯಲು ಎಲ್ಲರೊಂದಿಗೆ ಬೆರೆಯಲು, ಅರಿವಿನೂರಿಗೆ ತಿಳಿವ ತೇಜದಿ ಹೆಜ್ಜೆ ಹಾಕುವ ವೇಗದಿ, ಅರಿವಿನೂರಿಗೆ ತಿಳಿವ ತೇಜದಿ ಹೆಜ್ಜೆ ಹಾಕುವ ವೇಗದಿ, ಹೆಜ್ಜೆ ಹಾಕುವ ವೇಗದಿ. ನಿಯತಂ ಕುರು ಕರ್ಮ, 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 ನಿಯತಂ ಕುರು ಕರ್ಮ.
I now request Mr. Guru Prasad from the Department of Journalism to welcome the gathering. Guru Prasad, audio is muted. Can't hear. Guru Prasad, it is not audible. Please check the settings. Change the settings of audio. Hello?
Hello, Dr. Bharati.
Yes, sir.
So you don't wait for all those things. You
Okay,
just
shall I continue? Okay,
Yeah.
sir.
yeah. I'll do one thing. I'll just proceed. Right?
Yes, sir. Okay, sir.
Okay.
I'll just continue.
Yeah. Good morning, everybody.
Yes, sir.
Yeah, I have great pleasure that the Department of Computer Science of my college is taking a lot of initiative in keeping pace with the changes that are taking in the broader world outside. And of course, we are being extended all the facilities and the support by the University of Mangalore. I'm very glad to welcome Professor P.S. Edaparitaya, the Honorable Vice Chancellor of Mangalore University. Sir, a great welcome to you. I am very glad that we have a dynamic registrar, Professor Mr. Raju Mugavira, KAS, as a registrar of my university, who is in charge of all the administrative affairs. And it's my pleasure to welcome him to this program. And we have with us the other participants to this program who are very enthusiastic to know what are the changes that is taking place in the world of knowledge. Ultimately, it is the knowledge that guides the actions and activities of the greater world outside, be it any field of inquiry. So, a hearty welcome to all the participants to the webinar. And I'm very glad that Mr. Pratheek Irvathur has consented to be the resource person today. And a warm welcome to you, Mr. Pratheek.
Thank you, sir.
Thank you. And I'm very glad that Professor Veerbhadrappa, Dr. Bharati Pilar, Mr. Guru Prasad, and Sudhindra, a team which is behind this venture, needs to be congratulated, and I extend a welcome to them as well. Before the formal presentation begins, I would like to pass on the mic to Dr. Bharati Pilar. Bharati, over to you.
Okay, thank you, sir. Thank you for your welcome address. We extend our warm welcome to you as well. All birds find shelter during the rain, but eagle avoids rain by flying above the cloud. Problems are common, but attitude makes the difference. Our Honorable Vice Chancellor, Professor P. Subramania Edaparitaya, sir, is such an eminent personality. It's indeed pleasure to listen to Professor. Now, let us have inaugural address by Professor P. Subramania Edaparitaya, sir.
Mangalore University. I am very much pleased to know that the Department of Computer Science, in association with Internal Quality Assurance Cell of our University College Mangalore, is launching international webinar series on emerging trends in intelligent computing and informatics. This webinar series intends to cover the basics of cutting-edge technologies like artificial intelligence, machine learning, natural language processing, and biometrics. Episode 1 deals with application areas of artificial intelligence and machine learning and handled by Sri Pratheek Irvathur, NLmatics, New York, USA. Artificial intelligence and machine learning have the ability to transform every aspect of our lives, from automated driving to robots performing complex surgery. It is the branch of computer science that emphasizes on creating intelligent machines that work and react like humans. Intelligent machines have replaced human capabilities in many areas. The application of artificial intelligence and machine learning include personal assistants like Siri, Cortana, OK Google, prediction in financial sector and sales, healthcare, recommendation systems, surveillance systems, social media services, spam filtering, customer support, fraud detection, monitor the outbreak of disease like COVID-19 pandemic to stop its spread, and many more. There is already a huge demand for professionals who can utilize the power of machines for intelligent automation. As a matter of fact, the natural language processing based systems help the user to translate from one language to another, acting as machine translator. It also helps in dictation systems where the user speaks and the words spoken will be converted into text. On the other hand, machine learning is the technology which enables a machine to learn and adapt with past experience to tackle new problems. This deals with the building of machines that learns the trends from the current data and predicts outcomes for a new data. An artificial neural network is a machine learning algorithm based on the concept of a human neuron. Internet of Things is a system of interrelated computing devices, mechanical and digital machines, objects, animals or people that are provided with unique identifiers and the ability to transfer data over a network without requiring human to human or human to computer interaction. But there are a number of challenges, I am very sure. One of the major challenges in artificial intelligence and machine learning is data security. The decision-making ability of artificial intelligence and machine learning applications are based on huge volumes of classified data that are often sensitive and personal in nature. This makes it vulnerable to serious issues like data breach and identity theft. Anyway, all said and done, I congratulate and commend the efforts of Dr. Uday Kumar, the principal of our University College Mangalore, Dr. Veerabhadrappa, convener and IQAC coordinator, Department of Computer Science, and Dr. Bharati Pillar, coordinator and assistant professor, Department of Computer Science, University College Mangalore, for successfully organizing this international webinar series. Best wishes and good luck to all the online participants of this webinar series. Thank you very much for your time and opportunity.
Thank you, sir, for the fruitful and inspiring message. Principal, sir, shall I go ahead with the session, or are you giving one more speech?
No. We'll start the session. Yeah.
Yes, sir. Thank you, sir. Now we shall begin the session on application areas of artificial intelligence and machine learning by our resource person, Sri Pratheek Irvathur. Here is a short introduction of Pratheek Irvathur. Sri Pratheek Irvathur is a UX designer who works on creating data-driven user-centered design. His areas of interest is in application of machine learning, design pedagogy. He currently works at NLmatics, where he helps design the user experience and product features for natural language understanding based products. Participants, please note, you can type your doubts in Google chat window. Your doubts will be cleared by the resource person at the end of the session. I now request Prateek sir to begin with this session. Over to you, sir.
Thank you, Bharti ma'am. Can I present my screen?
Yeah.
Okay. Is it visible?
Yes, sir. It is visible.
Okay. So good morning, everyone. Thank you for joining us today. So I'll get right to the topic. So I'm basically going to be talking about the application areas as it's been introduced, but I think I would like to start by focusing a little bit on the concepts so that we kind of understand what exactly it's made of, what exactly we're dealing with here, so that we can better kind of understand the scope of how solutions can be applied. So through the next 1 hour, we'll be going over quickly the brief history of artificial intelligence and machine learning. And we're going to kind of try to understand what exactly is it made of, because it's a method, it's more of a discipline. It's not necessarily a single silver bullet to apply to any sort of problem. So thirdly, we understand sort of how does it work? Like how does it take the decisions that it takes? What are the different parts? So any sort of machinery, for example, also that you look at a machine that takes an input and gives you an output. You kind of need to understand what each part in it does. So that's kind of what we look at. And lastly, once we have a better conceptual understanding of what it's made of, how it works, then we can sort of go into what we can possibly do with it once we kind of understand everything that there is to it. So to start off with, even though AI and machine learning has been more of a buzzword recently in the past maybe 4 or 5 years, the history of the idea of machines carrying out intelligent actions traces all the way back to like the beginning of the 20th century, where science fiction sort of boomed, and that sort of set the initial seeds for this whole idea that intelligence can be offloaded to a machine and machines would eventually take over a lot of these activities that are considered to be uniquely human. So around 1950s or so, we have the Turing test, which is basically a test that Alan Turing, one of the founding fathers of computer science and information theory, came up with, which is basically a test that's used to distinguish between a human and a human-like intelligent computer. So that you can see is somewhere over here, 1950s. And then we sort of started picking up more and more because it was a whole new field that we just sort of explored. Computers were just becoming a thing. Of course, computers were much bigger back then. But the fact that there was a new way to look at data and a new kind of programming platform in the form of a computer to sort of
Hello.
work with that data led to a lot of exploration in the next few decades. And finally, in the 90s, in the late 80s to the early 90s, there was something called the AI winter, which was so basically we had explored a lot of new ground, but then we had sort of hit a dead end because of the technology that was available at the point, and also largely because of the perception around AI. I think AI had been sort of oversold at that point so much that people kind of had unrealistic expectations of what it can do. So there was like reduced interest in funding, just overall a lot of less work happening. But then once things like big data came about, once things like better computing platforms came about, especially the rise of, let's say, much cheaper forms of computation, whereas earlier supercomputers used to take like probably an entire hallway. We now had computers that were much more compact by the time we reached this era. So at this point, AI sort of starts picking up again, and then you have things like AI that plays chess and stuff with like Deep Blue, which was like considered one of the marking point. So if we kind of trace it back, this kind of work or endeavor to offload intelligent tasks to a machine has been happening for quite a while. So even the current state of AI sort of borrows a lot from the long history behind it. So, what exactly is AI? Because this kind of term is used a lot: artificial intelligence, machine learning, and it's also sort of used interchangeably. So, AI, it's funnily enough, there is actually still a lot of debate on what actually constitutes AI. But if you have to sort of go with the dictionary definition of it, it's something that it's basically a branch of computer science which helps you to develop a computer system instead of a single algorithm or a single component. It's more of a theory and development of a system that sort of is able to do tasks that are usually associated with human intelligence. Now, this is actually not very accurate per se, because we also kind of try to do machine learning and AI that relies on other forms of intelligence. But for the sake of clarity and for the purpose of our discussion here, we can sort of limit it to human intelligence. So when we say human intelligence, what do we mean? Now think of something that's like a young child or a baby. So you start understanding the world around you by perceiving. You understand that this is your dad, this is your mom. So there what you're doing is you're sort of classifying your visual information. You learn, you come up with abstract concepts, and then you sort of act upon them. You understand that, for example, fire is hot, you're not supposed to touch it. So that's a
Pratik
learning.
sir, sorry to
Yes,
disturb you.
yes.
Participants, in order to see Pratik sir's presentation, you have to click on the window Pratik presenting. There are two windows for Pratik sir. One is Pratik IE. If you click on Pratik IE, you can see, sir, your is not visible, sir. Your face is not visible in the Pratik IE window.
Oh,
Uh,
yes, yes.
your video is not visible. So Pratik eye window will show you the face of the person, whereas Pratik eye presenting will show you the presentation screen. We can see presentation screen because I have clicked eye presenting. Sorry, Mr. Sir, please continue.
Yeah, no problem. Thank you for that. So now we kind of, if you look at it, this is something that DARPA came up with. DARPA is basically the arm of the US government that has to do with defense research. And DARPA is something that's been heavily funding AI right from the initial days when the Defense Department was kind of interested in the application.
Pratik sir, your audio is muted.
Oh, I'm sorry about that.
Yeah,
Okay, so I can go back to this.
yeah,
So coming
yes.
back to it, DARPA is came up with this idea of four waves of AI. DARPA is the American government's arm of defense research, and they sort of heavily invested in AI and AI research and computation, with mainly because of interest in its military applications. And they have been sort of leading figures, one of the leading figures, I'd say, in funding AI research. And they kind of came up with this idea of four waves of AI. We are still in the learning phase, and it's sort of going to the context phase. So quickly to go through the four of them. So these are basically ways to understand the different forms in which AI came about, or rather, the different capabilities and the ways in which those capabilities are achieved by the AI. So the first thing would be reasoning, which is the first way of AI, where it could not do a lot of perceiving, but it could do reasoning. Now, what do we mean when we say reasoning? It means when you have a query, for example, that's posed to the system, it's able to reason what it needs to give back and then sort of provide an output. So it doesn't really perceive as much or learn or abstract or form concepts. Now, with learning systems, we were able to sort of to get an example of reasoning. For example, there's something called expert system that was introduced by Feigenbaum in the 1980s, and expert systems were basically uh, computational systems that collected knowledge from an expert, and there would be an engineer that sort of encodes this knowledge from an expert into a knowledge base. And any sort of user who wants to benefit from the expert's knowledge would submit a query, and the inference engine in the system, which does the core part, would sort of give you the output. So what it's doing mainly, again, if you look at it, the inference engine is what's doing the reasoning. Like the name suggests, it's inferring what needs to be provided based on all the different kinds of knowledge that it has. So it looks at the knowledge base, picks out something, gives it back. So now if you go back to the learning one, so this is what was enabled by lots of data, and especially with the rise of big data and the kind of data mining that happens today. I mean, pretty much, I think from the time you wake up in the morning to you go to sleep in the night, your phone itself connects so massive amounts of data on you. The way when you interact with the world, when you swipe your credit cards, any sort of interaction that you have where you're putting out any sort of data, just to get an idea, and there's so many people in the world, so you can just imagine the massive amounts of data that's being generated and the amount of data that's being held in all the servers across the world. So with this amount of data and with statistical methods applied, we were able to sort of come up with systems that could perceive as well as learn. Now, perceiving would happen through sensors, through different kind of structured and unstructured data. Structured data would be data that's, let's say, in neat tables, rows, column. Unstructured data is, let's say you look at a newspaper, everything is all over the place. You kind of need to look at it and make sense of it. So that would be an example of unstructured data. So it was able to perceive and learn. Now we are sort of in the point where we are kind of able to make it look like it's understanding contextual adaptation, which is where what we are actually doing is we are kind of using statistical methods along with a few other mathematical methods to make it look like it understands the context, but we're still a little far away from it. So this is kind of what we can do right now with the second wave. We can do stuff like classification. Now, when a human being looks at this, you basically look at the image of the cat, you understand where it's situated, you sort of build the context around it, and then you sort of deduce that it's a cat. You do not rely just on visual information to say that it's a cat or it's a dog or whatever it is. So the idea here is that it is not really understanding concept of a cat, but it's rather trying to understand the patterns, and it's trying to come up with idea of how do we say this, a pattern matching of the pixels. And it's very easy to fool these kind of, we have realized recently that it's very easy to fool these kind of pattern matching things, for example, because if you look at this image, now the algorithm recognizes the first image as a panda with around 60% confidence. Human would too. But let's say you add a little bit of the right kind of noise. Immediately, the picture doesn't change much to the human eye, but to the same exact algorithm, it immediately is identifying it now as a gibbon, a type of monkey, with even more confidence than that it had when it said this is a panda. So you can see that it's kind of easy to mess with its understanding of what a panda is. So this is kind of the issue with the second wave of AI that we have, that it's very good at matching certain things, matching patterns, like crunching large amounts of data. But when it comes to sort of having consistency, or when it comes to sort of having a conceptual understanding rather, it sort of fails. So if you showed it a picture of, let's say, so these are the kind of images that from a very interesting paper where the scientists were sort of able to come up with patterns that are falsely recognized by the AI as these specific objects with a very high degree of confidence. It says this is a rifle, this is a stethoscope, and we can clearly see that it's not. So this is kind of the issue with the second wave AI of where we currently are at in terms of the methods that we use, in terms of the knowledge graphs that we build. So whenever we think of looking at, let's say, an image and a label data. Like you might have seen on Facebook for a while, they had this thing where if there's a picture of a person, it draws a square around it and it says, is this person? So think of things like that. So now, like the general impression that might be given is that it sort of understands who it is, but it's really not doing that. It's sort of doing a pattern matching, which is why it gets it wrong a lot of times. So third wave AI would ideally look something like this. This again is from DARPA by John Launchberry. He was the head of DARPA when they came out with this 3 waves sort of idea. So what it would do is, so basically for this kind of thing, what you do is you show the algorithm tons and tons and tons and tons of pictures of what a panda looks like that understands a generalized pattern. So here you do something similar, but you create something like an explainable model. So there's this idea of explainable AI that's been catching, that's been picking up pace a lot of late. So here, if you show it a lot of pictures of a cat, it also sort of looks at you also sort of give it other pictures to understand the context. You sort of understand that this is what a cat is made of. That it has fur, it has whiskers, it has claws, it looks a certain way, it makes a certain sound. So think of how humans sort of try to come up with a concept. Now, all of this is sort of, remember, it's being sort of represented in a very concrete mathematical manner as well. So this always has to be sort of there in the back of our mind. Just like how an image is a set of pixel values, how would you sort of now come up with an embedding of an explanation or a concept? How do you represent a concept like this is a cat in a sufficient manner in mathematical terms? And when it says that this is a cat, when the AI that you made says this is a cat, it should be also able to explain why it's a cat. It should understand why it makes the decisions it does, which is not something that we currently have. So right now the AI is good at recognizing, classifying, taking decisions, but it's not so good at explaining its decisions. It's not so good at reasoning backwards. So this is ideally where would be sort of moving towards to get a rough idea. And so if you have to look at a general architecture of an AI system, not just an AI algorithm, mind you, but a system that utilizes AI and gives you some sort of output. So now all of this needs to be wrapped inside a certain system, which is, this is sort of roughly what it looks like. This is not a very hard and fast sort of structure. So the first thing would be you need data. You need lots and lots of data. And sadly, almost 80% of the work in any sort of machine learning system that you do would be working with making data, bringing it to the right form. Because computers, again, the way you feed, it's basically garbage in, garbage out. So you need to have the right kind of data. It needs to be labeled properly. You need to have everything in the same format. So, and you need to sort of also differentiate between structured, unstructured data. You need to sort of also rephrase the way you provide the data to the machine. For example, the simplest example, like we saw the image data, right? You would probably not necessarily feed images as they are to a machine learning algorithm when you do the training. You kind of do a whole pre-processing where you normalize the values, where you sort of adjust the color maps for it, you sort of adjust the illumination, you sort of try to bring a sort of uniformity to it. You try to bring a sort of structure to it. And from there, it sort of goes to the algorithms, which really depend on the problem that you're trying to solve. So if it's a problem where you kind of know what you want to get, you supervise the algorithm. If not, if you wanted to sort of figure out on its own, we'll come to these parts later. We'll go through them in more detail, the algorithms. For now, it's basically enough if you kind of look at it as the algorithms are basically the decision making, the brain of it. And once we have knowledge from the algorithm, like the data is now converted to information, it's fed into the algorithm, and the algorithm generates knowledge. Now, AI systems on their own, we don't really have artificial general intelligence yet, which is the kind of intelligence that people have. So we have algorithms that can generate knowledge, but not algorithms that can generate insight out of it. Now the difference is knowledge would be something like this has been the share price 52-week minimum, 52-week low at a 52-week high. Now the insight from that would have to be generated by the human. So there again, it becomes a question of how much work does the human has to do, how much work the machine has to do, and from there it goes to an actual implementation form. Ma'am, I'm sorry, I just need to. I'm having a bit of technical difficulty. I just need to grab a charger. Can I just take a minute, ma'am? Hello. Sorry about that, ma'am. I was having a bit of technical difficulty here. Uh, okay, so to continue with this, am I audible? Okay. Uh, so now all of this sort of needs to be wrapped within a framework called robust AI. I mean, it's again a variable term. So first thing is to make it explainable, which is you need to understand why it takes the decisions it does. It's not like a magical thing where you throw in data and it just comes up with a decision and you just take it for granted. So it needs to be explainable. And also this is where metrics and bias assessment comes in, which is you kind of measure how well it's doing, you kind of measure it for bias. Bias is actually, again, a very, very important focus of machine learning and AI. We'll come to that in terms of application. Just quickly to go over it, bias literally means like when we say human bias, not any other sort of bias in mathematical terms, but like cognitive biases of people. Like you might have social biases, you might have gender bias. So we're talking about that kind of bias. And then you need to verify it, validate it. You need to have security measures. And of course, as with any other sort of thing which has real world implications, you need to have policies around it. You need to have an ethical code. You need to have right kind of training and all this stuff. So now, in terms of infrastructure that we use, just to give like a better idea of what is used, this is probably not the most important slide, but yeah, so for data preparation, we do things like processing it, you do things like version control, which is figuring out how the data has changed over time. And then you do things like labeling. Labeling is basically like you show it a picture and then you say what it's associated with. Like what do you want to click when you show it that picture or when you show it that specific data point. Then you build models, push them into production. So these are basically all the different platforms that are available. Now the point is not really to point out the platforms, but just to show that there's multitude of platforms available. So it really boils down again to the kind of problem you want to solve, the language you're working with, the library you're working with. So now to kind of go over it quickly. So artificial intelligence is the general idea. It really needn't have any learning or anything of that sort. It basically is just intelligent. That's it. Now, machine learning is sort of like the subset, which would be there's some sort of learning that happens. There's some sort of building up of a learning system that happens. There is some sort of feedback. There is some sort of improvement with new results. Deep learning is more of a subset of machine learning itself, which is where we sort of use things like neural networks and deep neural nets to sort of solve very specific problems. Now, what kind of problems are they used to solve for? We'll come to next. So now, focusing specifically on machine learning, because AI has been around for a while. Machine learning is what is sort of picking up since we have GPTs and GPUs and all sorts of new hardware that makes it available to learn. Now, let's say you have data with labels, right? So data with labels would be I'm going to again go back to the image thing because it's sort of easy. So data with labels, you would sort of show it a lot of pictures, for example, and say this is what it is. And this is what I should get as an output. Now, for example, you can think of something like an autonomous vehicle that has to read traffic signs, right? It looks at a traffic sign and it needs to give a signal saying you need to lower your speed limit, or you need to sort of maybe stop the car. So that is sort of, it sees a data with a label and it gives you an output. So it maps it. And when it gets it wrong, it kind of logs that error. It figures out by how much it needs to change the input in order to get the right input. So it basically has like there's a supervision that happens. You tell the algorithm this is right, this is not. And based on that, it figures out how to do it. Now, data without labels is basically you just have a lot of data. You need to figure out how to group it. It's like almost like giving someone a whole bunch of books or objects and saying, now make something out of it. Now, with reinforcement learning, it might seem a little similar to supervised learning, but the thing is here you are not really giving a error correction signal per se, but you're sort of giving a reinforcement signal. Now, reinforcement signals can either be positive or negative. So that kind of is a key point here. You can either have, you keep hearing things like positive reinforcement, negative reinforcement. So that's kind of what happens here. When the system does something good, you give it a reward. When it does something bad, you sort of penalize it in some way. So traditional programming, in a sense, you give it a data and you write the program, you hard code it, and you give it to the computer, and it gives you an output. So it's basically like, it's just clearly is solving, putting the data and the program together and creating computations and giving you an output. Now with machine learning, what we do is we kind of give it data, we tell it what the output looks like, and then we ask it to figure out what the relationship is. What is the program that has to be made, which when the data is passed through, gives us this specific output. So this is kind of, I would say, is one of the key slides in the presentation. And to, again, I seem to have a liking for cats and dog pictures for machine learning algorithms. So if you look at supervised machine learning algorithms, you can see that it sort of labels it, looks at thousands of pictures of cats and dogs, and it's able to distinguish what's a dog and what's a cat. Unsupervised, an example would be you go with tons of pictures of different animals, tries to find patterns and group them. It puts dogs, cats, giraffes all in their own bins. Now, the issue with coming up with, let's say, a specific application for machine learning is pretty much like saying an application for maths or an application for accounts. It's immense. It's a field that is just starting out. So you can see that the techniques of machine learning techniques themselves are immense, like so many of them. Things like classification. Classification is basically where you have things that you need to put into groups. It's as simple as that. Regression is where you sort of try to understand the relationship between an input and output, where you have things like linear regression, nonlinear regression, where there's a linear relationship between the input and the output, nonlinear relationship. And you have something like dimensionality reduction and clustering. So these kind of things come under unsupervised. Now, if you look at the middle part, there are a lot of methods that sort of work well for supervised and unsupervised learning. So these are just really, they depend on what kind of problem you're solving. For example, if I was using neural nets, I could probably use it for both supervised and unsupervised, but I would be using a different kind of neural network for each. We'll look into this when we sort of pick up neural networks specifically. And with reinforcement, you have things like Q-learning, Markov decision process. Markov decision process is something that a lot of people might have worked with, which is basically like you take the previous state and you try to sort of understand the next state and try to sort of build up a chain of events, try to come up with a causal set of events. So that's kind of how it works. Now let's move on to sort of neural networks. Now, the very basic idea of a neural network was a perceptron. Now, this is sort of based on the idea of a neuron in a biological equivalent. Uh, so what it does is it takes inputs and gives an output. I mean, simple enough. It's just like any function you might say. And that's pretty much what it is. It is literally a function which can take multiple inputs and give an output. Now, a perceptron is a single neuron which gives an output of 0 or 1. Now, you can sort of take the 0 as 1 as a confidence of the answer being not right as 0, or a 100% confidence as 1. I mean, it could be mapped to pretty much anything you want, but you can sort of take it like that. And how do we decide how does the perceptron decide whether the output is a 0 or 1? Now, what it does, it has a certain threshold. And if it's greater than the threshold, the summation of the weights and the inputs, then it gives you a 0. And if it's greater than that, it gives you a 1. Now, what do we mean by this little equation here, summation of wj xj? So what it does is, let's say each input is sort of given a weightage. Let's say there are 3 inputs, x1, x2, x3. Now, all inputs are not necessarily taken with the same degree of importance. So they are given something called a weight, which is basically like a degree of importance. So let's say the inputs x1, x2, x3 are all equal to 1, but the weights are 1, 2, and 3. In that case, x3 would sort of have a greater weightage because its weight is higher. So now imagine like a network of these, each with a different sort of function, right? So each one has its own input, each has its weight, and then it has a function that sort of decides how to process that thing. And the activation function is basically whether it's a 0 or 1. And the output function is the actual 0 or 1. So now if we sort of go back to this, it's pretty much the same as this. It's just a little more complicated than that in terms of the setup, but the basic unit still remains equally simple. So if you just want to put numbers to it, let's say you take the sigmoid function as the hypothesis function, and these are the 3 weights, minus 0.06. These are the 3 inputs, minus 0.06, 2.5, and 1.4. And these are the 3 weights of these inputs. So minus 0.06 is going to be multiplied 2.7 times, 2.5 is going to be multiplied 8.6, 1.4, 0.02. So the idea would be that the third weight has the least amount of importance. The third input rather has the least amount of importance because it carries the least amount of weight. So even if the value of this input was, let's say, 20, it definitely wouldn't carry as much of weightage in the entire operation as the second weight because of how much it accounts to. So now if the threshold is, let's say, 10, we decide that the output should be 1 because this output is greater than 10. So now this kind of structures can do an amazing number of things. They can do things like, this is one of the earliest examples of handwritten digit recognition. So this is from a data set called MNIST, which is basically labeled data sets of handwritten digits and their actual values. So all of these are, the first row is labeled as 0, 1, 2, 3. So the output here actually has 10 neurons. And based on which one fires, you figure out what the written digit is. So you basically give it an input, one of these handwritten digits, and it will either fire neuron number 0, 1, 2, 3, 4. And that output sort of figures out what digit was input. So this, I think, is actually a very good GIF of how it works. So you can see that the input here is 1, and the neuron that fires will be corresponding. Basically here 4, and neuron that fires is 4. So these are what all the different layers in between are sort of look like when they're visualized. And these layers sort of pick up on different kind of features of the input image. So neural networks again is like a vast, very vast area to explore. So now each of these cells that you saw basically can have their own behavior. Like a perceptron, like you saw, is the simplest thing, the first one over here, the two yellows and the single orange. Something like a feed forward network would probably have hidden cells, and it sort of feeds the information forward into the network, which is like it decides what to do, and it decides what to do by measuring its progress as it moves across the layers. Now something like a backpropagation network will look at how it should vary the weights by looking at the output and sort of trying to tweak each preceding layer. So it would basically look at the output, then look at the immediate layer right before it and figure out how to tweak that. And based on that, you go back one step. So it's kind of like reverse engineering it when you have a back propagation. You also have things like shape vector machines, which is basically a way to classify. So let's say you have data points. Now this graph on its own actually may not say much. It's basically what you have is, let's think of the line in the center that's got these two dotted lines on either side as something that carries out the action of dividing the plot into two areas. Now the red dots and the green dots are basically the two kinds of data sets. I mean, sorry, the two values that the variables can take, let's say, and it kind of tries to classify them into two sort of categories. Now, a real world example would be something like, let's say you want to deduce whether a tumor is benign or malignant based on the size of the nuclei and the uniformity of the cell size. Now we kind of have a rough idea of where each of these data points fall, but you're not really sure how to classify it. As in, if I have a new sample that is composed of two data points, the bare nuclear size and the uniformity of cell size, I want to know whether it's benign or malignant. So the shape vector machine will sort of help me figure out that demarcation, that area into which each of those data points should fall, and it helps us figure out whether it should be benign or it should be malignant. So here you can see that you're not really telling it what to do per se, it's kind of figuring out the clusters on its own. So now the common issues that you can sort of face. So now these are literally just three of there's just three of the many algorithms that are there. Now a lot of things can go wrong with this. Just a second, sorry. Yeah, so a lot of things can go wrong with this. You can underfit the data or overfit the data, which is you fit the data so well to what you train it with that it can't see anything beyond that. Or you kind of try to generalize it so much, you leave so much of gap that you kind of are not really able to be precise. The other thing might be bad data. Now, bad data is actually a very huge problem, which is the thing that what do you call it? Now I think people are having some technical issues. Okay, so the other thing would be bad data, where your data itself is sort of flawed, biased, it's not collected properly, you have not done sampling right, you have sort of cherry picked your data. So the machine learning algorithm's entire world is just the data that you feed it. That's how it understands the world. So you give it bad data, it's going to like sort of give you bad outputs. Next would be the model selection. So you sort of pick the wrong model itself to begin with. Like if you're working with, let's say, a linear system and you sort of pick a non-linear model to work with, it's obviously not going to give you the right output. You could ignore also the sort of edge cases or cases that you don't really account for. For example, if you are trying to you're trying to come up with a self-driving car and you only account for it driving on highways and not within city limits, that's going to give you a lot of issues. The other thing that Hold on. Is it visible now?
Yeah.
Okay, sorry about that. So these are the benign and malignant cancer that I was talking about. If you can look at, I can just quickly go over the last couple of slides again, just since it wasn't visible. Uh, okay, so let's just quickly go over it. I'm really sorry about that. So this was the MNIST database where I said it kind of picks out handwritten digits. So these are the digits. This is a neural network. These are basically, think of these as the 10 neurons that fire. I think if we go to this GIF, it's kind of easier to understand. Let me just quickly explain what's happening here again. This is the input, and this is the corresponding neuron that fires. So the neurons are from 0 to 9, and each neuron corresponds to the number that it sort of thinks is being shown. So if neuron number 7 fires, it means the input is 7. So and these are sort of the features that it picks up in between when it is going over the steps. So these are the different kind of neural networks that are sort of there. The perceptron that we went over is the simplest sort of form of neural network. Whereas if you kind of look at other structures, you can kind of think of each of these cells. For example, this blue one with the circle inside is called a memory cell. So it sort of holds the state. Something that's like a gated memory cell holds memory in a conditional manner. There's a backfed input cell, which is basically, it tries to figure out what's happening in the next step, and it tries to sort of adjust itself accordingly. So now remember, these are behaviors of individual neurons. And when you connect them together, when you sort of direct the output of one to the output of another, it sort of gives you amazing behavior. So this is quickly to go over the idea of classifying what can be a benign tumor or what can be a malignant tumor by just giving it the 2 data points of bare nuclei and uniformity of cell size. So what you're doing is you're just giving it these 2 data points, tons and tons of examples, and saying this is benign, this is malignant. And then you sort of let the machine come up with how those clusters are distributed along this graph. Like you can see that it can be a polyboundary, or it can be like a much more complicated, let's say a 3rd degree equation. So now the common issues, I think there weren't really any images, so I can go again to the next one. So these are kind of the common issues that you might sort of usually face. Now to go to the applications. Now, when we think of applications, normally the approach might be that we just take the principles and we figure out what problem can be used to solve it. We kind of very rarely tend to look at the tools themselves. We kind of very rarely try to look at whether the system that we're using is itself free of any errors. So since we're at this stage where we are sort of framing the 3rd wave AI, where we are sort of coming to understand how to build context, how to build the idea of a concept, we kind of need to also address the tools themselves. Now, this would be the first one of the projects that I worked on, which had to do with an algorithm called Compass. So what Compass does is it's used in courts in the US for figuring out the bail and sentencing of someone who is standing trial. Now, ideally, what it should do is it should just take the person's crime and previous, maybe if it exists a previous record and stuff into account, and it should basically give a fair output. But what it ended up doing was it had a lot of racial bias, and it sort of penalized minorities much more than it did white people. So now, why was this happening? Why is it that a machine learning system that has no real human behavior, one might think, doing this kind of behavior? Like if you see, it marked a person with the exact same crime and with much less, sometimes in a lot of cases, even with much lesser prior offenses with no prior offenses, in fact, and no subsequent offenses, it marked them as being much higher risk, which led to greater sentencing and a higher bail amount for them. Now, why did this happen? It happened because a lot of these, what did it take as inputs? It's kind of important for us to understand what inputs it took. So what happened was the person had to sort of answer a questionnaire with a lot of these questions that sort of worked as proxies for race, that sort of worked as not direct indicators of race, but were sort of indirect indicators of race based on, let's say, your locality and something like, let's say, your friends or your acquaintances. So that could also sort of really boil down to where you live, what kind of socioeconomic conditions you live. And these are all sort of very intersectional topics, and it's very difficult to sort of just put this out in a black and white manner. Now, this is something that Google came up with once it realized that we've had a very long history of having very biased data sets. For example, if you look at the film that is used to do photography, I mean, it's making a comeback now, but if you look at something like that, the history of film itself has like a very racist history to it, where the film was sort of manufactured to best reproduce the color skin tones of white people or Europeans' skin tones much better than it was supposed to. Like, it wasn't even made to reproduce the skin tones of anyone besides European skin tones. So the entire product itself, you can imagine, is something that is developed keeping a certain population in mind, that's kept developed keeping a certain intention or a prejudice in mind. So these, if you look at this, basically these are all the places where human bias can creep in, right? From collecting data to how we label data, right? So do you label some kinds of data as, let's say, very hard to sort of make a risk assessment, for example, right? Do you sort of make a risk assessment based on your prejudices when you label it? If so, algorithm picks up on it. And also, how do you sort of choose the metrics, right? In an industrialist society, in a society where, let's say, an individual's soul worth is decided by the capital gains that they can produce, the kind of metrics that you use to train a system might be very, very limiting. If you don't, let's say, take into account maybe a different, more encompassing management theory, for example, to evaluate employee performance, which was actually what happened with one of the models that was used to evaluate a teacher's performance. And they didn't really take into account things like student satisfaction or anything of that sort. All they took into account was scores of the test scores of those students, and that produced a very, very skewed model. It produced some disastrous results in the long term. So the kind of product that we came up with, I can't really share the exact product here because of copyright and some other issues. So the kind of product that we came up with was, I can just talk about it in a very rough way. So the product that I came up with had to do with a metric to measure bias. And what it did was it kind of created a biased model. So let's say you don't want a model that's very racist, right? Or you don't want a model that's very sexist. So then what you do in this approach that we developed was that you intentionally create a biased model so that you have something to benchmark it against. Otherwise, you're kind of trying to benchmark it against a non-existent measure, because human bias is always going to be there. How do you find a person without bias to do these tasks? The idea is that bias is always going to be there. How do you sort of identify it and reduce it? So what we did was I created something for Compass, which on purpose penalized minorities. And then we sort of evaluated the performance of Compass itself. And when we found that the evaluation of Compass is very similar to AI that's made bad on purpose, then we sort of have an understanding of whether it's really acting in a biased way. The other application that I worked on was called Saral. This was a product that I was working on for the Ministry of Health. It didn't come through in the end, but this was back in 2015 when the H1N1 flu was epidemic was spreading. So this was where we sort of used crowdsourced government data. So we to build like a global model. So now normally what happens is a person like a medical professional, he goes to a site of outbreak and they sort of study how many people have the disease, what are the specific cases like, and let's say someone else from another department in the government, like the census, they have a very different kind of data. Let's say the veterinary department has another kind of data. So our government collects a massive amount of data. And I think if anyone's interested, this would actually be a great thing to look into. Data.gov.in, I can drop that in the messages. So you just go to like this website, you'll find tons and tons of government data by the Indian government. And cross-referencing them after processing them right, I was able to come up with a sort of a machine learning and visualization module, which sort of took the output as the incidence of an epidemic in any given location, that in this particular tehsil or district, in so many cases, another one so many, this is the particular demographic of this district. So how do we sort of understand? Is there any relationship between the socioeconomic factors? Is there any relationship between the epidemic spread and, let's say, the gender ratio of the area, right? So we basically kind of bring together all this data together and we throw it into a machine learning backend, which has, let's say, something like an unsupervised problem, for learning model, for example, and it helps you sort of make sense of this data. So what we did was we sort of didn't try to make sense of this data in a direct quantitative manner, but we sort of visualized it spatially. This is the incidence data. The bars basically give you the height of the incidence data. And we cross-referenced this with a lot of other kind of data like the census data and like the socioeconomic indicators, the urban density. So things like that. We even took into account things like transportation routes. So, and then we were able to come up with this sort of modeling that gave a time series prediction of how the epidemic would spread. So this kind of helps us to also, so this is basically the knowledge that we're talking about, right? Now, as human beings that work in tandem with machine learning systems, we kind of, it's our job to now produce insights from it. So if this is the kind of spread that happens, it's the human being who next has to take the decision. So what should the next decision in the solution be? Should it be how do we sort of optimize our testing centers better? Instead of just scaling up testing, can we do testing at the right locations to sort of monitor the disease? Or maybe from here, we could go into something that maybe looks at all the tweets or maybe looks at activity in social media and tries to sort of correlate that. So once we have this knowledge, there's tons of things we can do to generate insight. Now, the kind of thing that I'm also sort of interested in is design pedagogy and coming up with knowledge systems, which is to sort of understand the context building. That's the third wave of AI that we were sort of talking about. Now, these images probably don't make a lot of sense because that's kind of, I guess, the intention. It's a product called Artbreeder. In fact, we have products now that use machine learning. We've reached that stage where it's pretty widespread, right? So when I say product, what I mean is machine learning as a tool is accessible to us now. So I can actually just do a very quick demo of it, just to give a rough idea. I'll stop presenting for a second. Please bear with me. Stop presenting.
Audience, any questions? If you have any questions, please put it in the chat window.
So let's just quickly do a training. So this is everyone able to see the screen called Teachable Machine? Okay, great. So now let's do like a basic super quick classifier, right? I mean, this is a bit gimmicky, but it just gives you a good idea of how to do this. So What this basically does is it takes images and then it tells you which image is being shown. Now the thing is, you can map, once you have that input, I mean the output of this is being shown, you can use that to trigger basically anything that you want, right? So let's sort of train it to recognize some objects. What do I have here? Okay, so let's just try, like I'm basically trying to show it a calculator. Got like 17 samples. Let me just
ನೀವು ಅಷ್ಟೇ ನಿಮಿಷ ಮಾತಾಡ್ತೀವಿ ಆಯ್ತಾ ಇದು ಇದ್ದ ಎಲ್ಲ
rotate it a
ಪ್ರಿಂಟ್ ಔಟ್.
bit. And okay, so now let's try to do a second class of objects, right? So now we've sort of trained it we've sort of put in data of what a calculator looks like. Now let's try to sort of maybe train it with the data of a watch and sort of do that. And now we can sort of train our model. That's how easy it has become these days to sort of actually do this train data. So while it trains, I can probably take any questions. Yeah, so convoluted CNNs are basically a kind of neural networks. They use something called okay, I'll get back to that. Let me just finish the demo. I can take the question right after that. Sorry about that. So now when you take the watch, it's confident. So this class 2 is basically watch and class 1 is the calculator. So now when I show the watch, you can see clearly that it shows class 1. Now when I show the calculator, you can see that class 1, it shows it confidently as 100%. So watch, it shows class 2, calculator, it again shows 100%, right? So, and now what you can do is once you train the model, you can actually like export the model. And this is pretty amazing that you can actually export it as JavaScript. And I mean, if anyone's familiar with code, I can actually just quickly do this. So you have this output here called class prediction. Once you have this as a number between 0 to 100, you know that you can map it to pretty much anything else. You can map it to something like when I show it a watch, I wanted to, let's say, play a certain sound. I wanted to do a diagnosis. I wanted to do something else. So that's kind of amazing. And this is something called a Hugging Face transformer, which helps you in complete text. This uses a model called Distal GPT-2, which is a natural language processing model. So I think because of time constraint, I'll have to sort of get back to, yeah. So we have, so can I start taking questions now? Okay. Okay, so there's two questions. May I know about CNN and how is AI helping COVID-19 pandemic? Okay, so the first one, CNN. I can actually go back to the slide that I had about CNN. Window. Similar 12.
Prateek sir,
Yeah.
your face is not visible. Can you switch on the camera, please?
Oh yeah, sure. Sorry. Okay. So, all right. So going to this CNN. All right. So you can sort of look at this neural networks, right? So a CNN is basically something like this. So you have a single perceptron, right? Now, what a convolutional neural network does is it's basically just something that uses that and operates over a volume of those. So it kind of takes all these inputs, and let's say you take this second layer of neurons. You can see that each neuron here is kind of getting inputs from the previous layer of neurons. Like each one of these perceptrons is sort of sending out outputs each of the neurons in the second layer. So it's kind of like this mesh of inputs and outputs where each input and output is sort of adjusted, fine-tuned, so that the network as a whole sort of gives you the right output. So that's like a very basic idea of a CNN, but I can send material in case anyone is interested, or you can email me at any point. I can put out my email and feel free to reach out to me. Uh, how is AI helping COVID-19 pandemic? Quite a bit, actually. In fact, companies are also sort of working with this. We take tons and tons of unstructured data, which is reports from world over, like PDFs. We just throw in thousands of these PDFs into this processing engine, and it kind of understands the concepts and even things that are not literally spelled out. So you can ask it questions and it sort of helps us identify symptoms, it helps us identify spread. AI is also helping us sort of come up with new drugs by sort of reduce testing, optimize testing. AI taking over human within the next 2 decades, I think, would be highly improbable, because for that we need something called generalized AI, which is what we have right now is called narrow AI, which is the second wave. It has mostly statistical methods. It doesn't have explainable models. So there's a very, very long way to go before we can come up with general AI, which has literally human-like capabilities. And I mean, there's a lot of work happening, and it's also sort of unpredictable. But taking over is definitely not possible, because AI is sort of very, very specific in its input and output. So that sort of contextual concept building wiggle space is sort of absent right now, and we still haven't figured out how to do that. There's a recent work on COVID. They have worked based on X-ray image. Does AI play an important role there? I'm not familiar with this paper, but it's definitely possible to use AI there. But again, it really depends on whether the problem warrants the use of AI. Like, do you really have such a huge data set that you can learn from? Or is it something that's very simple AI classification? I'm not really aware of what specific methodology they have used in that paper. So I think if I take a look at the paper, I can definitely help. So if you can link the paper, I can definitely take a look right now. So it looks like I actually found the paper on Arxiv. It's called Automatic Detection of COVID using X-rays and deep convolutional neural networks. Yeah, so they are actually using CNNs, which we just explained. We can actually just share the screen here. So I think this is the paper, right? Represented just images, so you can clearly see some sort of different. Okay, so what they have done here is they have loaded like these pre-trained models called ResNet. ResNet is actually already available. You kind of need to tune it. So they've used pre-existing deep learning models, CNNs, and they're done tracing. And yeah, so basically what they have done here is classification, whether the image shows a COVID-19 X-ray or it shows a normal X-ray. So this is again like classification based on labeling. And oh, it doesn't seem to be based on labeling. It's based on unsupervised learning. Yeah, so it does play an important role, it turns out.
Any other questions? Okay, one more. Is there any information?
Yeah, so I'm not actually very familiar. All I know is that it's kind of CNN again, and I remember it was used for image recognition, but it's a kind of deep convolutional neural network. So that would kind of fall into the deep learning part. So NLP, how is it used in chatbots? So I think one of the main challenges in using chatbots is sort of understanding how a conversation builds up. You can actually check something called GPT-3 right now. GPT-3. It's got something called the AI philosopher. Uh, so what the main way NLP is sort of being used right now, one of the main challenges being solved is sort of being able to maintain the thread of conversation. Like you start off by saying, "Hi, this is what I'm doing," and then the chatbot says, "Okay, so do you need any help with what you're doing?" Then you say, "No, I don't need help, but can you give me some more ideas?" Uh, and at this point, the AI is probably going to ask you ideas for what. So it's kind of lost the thread of conversation about what we were speaking, let's say 4 or 5 sentences before. So that kind of thing is also like still very difficult to kind of understand what is actually happening. Where is that question coming from? Hidden risks for AI, definitely like the bias that we went over. This was something that people glossed over and didn't really pay any attention to for a very long time. Uh, Other than that, there's always the risks of not picking up the right model. The risks would mostly be on the human end, I would say, about of making the wrong or insufficient demand. It's kind of like those stories where you make 3 wishes to a jinn and it kind of finds that grammatical loophole to give you something that you asked for but something that you didn't really have in mind. So that would kind of be like a hidden risk for AI. So any more questions?
Any more questions? Any other questions? Please type it in the chat window of Google Meet. Is there any question which is unanswered or skipped by mistake? One more question. What? Wait, okay. Yeah, slowly type.
Yeah, no problem.
Wait, is
Take your time.
typing.
Yeah. Yeah. No, I highly doubt GPT-3 will replace programmers because even now people have immensely more potential than now. Programmers, again, like it might be able to sort of automate the writing of code, but coming up with the idea of code and bug fixes, even now on a daily basis, we probably fix a lot of bugs. So even though we use machine learning as a code product, and GPT-3 is something that we've actually been looking at, and it's I don't think it's going to replace programmers. We have high resolution cameras, but how can AI be used in this area? So AI can be used in this area. China sort of does this. A lot of other countries do it. US does it. Basically, almost any country that has traffic cameras sort of does it. I think India has also started. There we have vendors that sort of are selling products like this. So what it does is it does character recognition. So AI can use it for character recognition. But yeah, I mean, that's one of the most simple ways we can, like, you don't necessarily need a high resolution camera, but even with, let's say, a VGA camera, it's the steps would be take the image, uh, break it down into like pixel values, minimum amount of information needed, pass it through like a classification thing, and that's probably one of the ways you could do it. What do you think about image computing with respect to feature extraction and data segmentation? Uh, I think, I mean, this not much, I think, but I can give you like my experience with it. So with feature extraction, one of the projects that I worked on was coming up with feature extraction from aerial images of urban areas to sort of understand how conflict spreads within urban areas when there's a riot or something of that sort. So it's kind of interesting to look at what kind of features the algorithm picks up on. That's kind of always been fascinating to look at. So what happens is like with the MNIST data, digit recognition, for example. Like let's say you write a 9, it's made up of a loop and a line, right? So as you sort of move on, it kind of gives you these, it recognizes those individual features. And feature extraction now is one of the approaches rather to understanding an image as a sum of its parts. But is there any other way to sort of explore it? It's still like coming up. Dataset generation, we also use it for dataset generation. I had used, I think, a DC-GAN, which is a direct convolutional generative adversarial networks. Long name, but all it does is conducts two things that compete with each other and makes two things win out in the computation to sort of create a better output. So dataset generation, it's definitely like a huge advantage that we have. Yeah, so I think dataset generation has actually been like a huge benefit for us.
Anything else? Participants? How was it? You can comment in the chat window.
So if anyone wants to reach out to me also, you can just reach out to me. I can put my email address. So in case anyone wants to like reach out, put my email address in the chat window. If there are any more questions, I'd be happy to answer them the next couple of days. Welcome. Thank you everyone for coming and for your interest.
Okay. I think no more questions.
Hello.
Thank you, Pratheek sir. It was indeed a very interesting and knowledgeable session. The number of questions that the participants were asking itself shows how attentive they were throughout the session. I'm pretty sure that all the participants have been benefited by your informative session. We wish to see you once again in our future programs. Thank you very much.
Thank you. Thank you, ma'am, for having me.
Mr. Sudhindra, please put feedback link in Google chat as well as in the WhatsApp groups. Yeah, it's already put. Your participants, please fill the feedback form and submit. On this occasion, it gives me immense pleasure to thank our Honorable Vice Chancellor, Professor P. Subramanya Yedapatitaya, sir, Registrar of Mangalore University, Sri Raju Magavira, and our Principal, Dr. Uday Kumar MA, for the constant support and encouragement. I extend my thanks to our HOD, Dr. Veerabhadrappa, sir, and Dr. Rajalakshmi Madam from the Department of English for the active support and suggestions. I would like to thank Mr. Guru Prasad, Mr. Sudhindra, and Mr. Ronald Nazrat for the technical support. I also thank all my teachers, my colleagues, and the participants for their active support. Thank you one and all. We are concluding the program.
Also, sorry, ma'am. Last thing, someone's asked to share the presentation PPT, so I can send it to Bharti, ma'am, and I can make probably put a public link. Yeah, I'm more than happy to share the presentation.
Okay, sir. Sir will send the presentation to me and I will share it with you. And one more thing, we have YouTube streaming. That video we will edit, and Prateek sir's presentation video we will share it in the group as well as in our college website. Thank you very much.